Alright, so let's talk about the running time and analyzing the running time of quick select. So just like in quicksort, our hope is that we get a pivot choice that's good enough often enough. So our theorem is going to be for every input array, the average running time of quick select is big O of n. So on average, we can return the ith order statistic in linear time. So again, here's our code for randomized selection or quick select, depending on how you want to name it. Where is all the work done? Well, we've got our constant amount of work here, and essentially a constant amount of work to have these function calls here. Move pivot to the left should be a constant amount of work, so that leaves partition. So most of our work is done here inside partition. All right, specifically, where's all the work done in partition? Almost all the work is done in this for loop again. Okay, so we know that all the work is done in partition, and the total amount of work done in a single call to partition is some constant times n. It's a linear amount of work. Okay, so that's the information we have at our disposal here to begin with. Let's add some notation so that we can talk a little bit about more, because we know each time we call partition, we're giving it a different amount of work. Let's add some notation that tells us sort of what n is at any given call. So let's say that quick select, randomized select, R select, is in phase j if the current subarray size is between n times 3/4 to the j plus 1 and n times 3/4 to the j. So I want you to pause the video and just make sense of that inequality on this line here. Okay, so what do I mean by subarray? I mean the elements we're currently looking on that are in this span, from right index minus left index. So to start out with, that's going to be all elements. So when we have 100% of the elements, that's going to be called phase 0. So if you take this side of the equation and you raise it to the 0 power, so 3/4 to the 0 power is 1, and we have that our subarray size is less than or equal to 1, and it's greater than or equal to, well, what do we plug in? What if we plug in 0 into this side? That's 75% of the input. So 3/4 of the input, so j plus 1 is 1, 3/4 of the 1 is 3/4, so n times 3/4, 75% of the input. So phase j is when we have anywhere from 75% to 100% of the input. Phase 1 is when we have 56% of the input up to 75% of the input. And I'm now realizing this should be not less than or equal to, this should just be less than. That's a mistake on my slide here, sorry about that. And how do we end up with this 56%? Well, if you plug in a 1 here, 3/4 squared gives you this 56%. And then phase 2 is in this range, and phase 3 is in this range. So that's kind of abstract. Let me try to make it a little more concrete by giving you some pictures. Actually, before I do want to make these 2 points. We can have multiple recursive calls, so multiple calls to partition that are in the same phase. So let's say we pick the maximum element. We had 100% of the elements, and let's say we had 100 elements to begin with. So we have 100% of 100 elements. We pick the maximum element, and now we have n minus 1 element, so 99. We're still in this 75% to 100% of the elements range. In fact, we have 99% of the elements. So we can have multiple recursive calls that happen in the same phase, and then sometimes a phase can be skipped. So if I get really lucky and I whittle this down to just having, let's say I'm looking for the first order statistic, just as an example, let's say I'm looking for I is equal to 1, and let's say the pivot element that I pick is happens to be at index 5, and I have 100 total elements. That means I only have 5 elements that I'm looking at. That means I have less than 5%, and I've skipped over all of these other phases. So I can skip over phases, and I can have multiple recursive calls into the same phase. Let me be a little more concrete and show you what some of these look like. So to be in phase 0 here at the top, I could have all my elements. I could have picked, I don't know, for example, this element and gotten rid of the 2 above it, but maybe the order statistic I'm looking for is still over here. So that would still put me in phase 0. I could do the same thing on the bottom end, or I could have picked the maximum element as the pivot and the minimum the minimum element and the maximum element as the pivot. And after 2 calls, I'd still have in that range of 75% to 100% of all my elements, and I'd still be in phase 0. To be in phase 1, I could have picked this element as the pivot. I could have picked this element, or I could have had 2 pivot elements and ended up there. So there's a lot of different ways I could be in phase 0, a lot of different ways I could be in phase 1. Same thing for phase 2, phase 3, phase 4, and so on until I don't have enough elements left to create its own sort of phase number. Okay, well, like I said, multiple recursive calls can be made in the same phase. Some recursive calls can skip over the phase. I'm going to add some new notation here. We're going to say xj, and that's going to be the number of recursive calls made during a phase. So back to here, how many times am I stuck in phase 0? How many times am I stuck in phase 1, and so on. xj tells us how many times we're stuck in phase j. And remember, each time we're stuck in phase j, we have a call to partition. So given that information, what is the total running time of quick select, also known as rselect, or randomized selection? So instead of putting an extra insert into the video here where you answer a question, we'll just answer this question at the start of the next video.